Okay, so welcome everybody to Linux Tools for Text Processing. There are a few links here. If you go to the bit.ly link, you can get a copy of the slides. And I added another GitHub repo here. So the first one, SDSC Complex Linux Text Tools, has the examples that we're working through today in the webinar. But I realized there's a lot of material. It's really way too much to squeeze into essentially a 45-minute webinar. So I've been developing a Coursera class on the side, not quite launched yet. But if you go to this bottom link here, the Syncovate Coursera Linux Tools, you will see a lot more examples that you can work through if you feel like you'd like to go a little bit deeper. So, always like to mention our NSF funding. We are an NSF funded project focusing on the non-programming skills that we think that you need to effectively use supercomputers. And I think a lot of you are already familiar with the topics. So let's dive right in. Here's what we're going to be covering today. Give a little bit of an introduction, then dive into head and tail, paste, NL, sort and shuff, split, grep, sed, awk. And if we have time, we're going to look at a few case studies. So a little bit background, a little bit of motivation for this, for this particular lecture. So I like to say this session is intended for anyone who needs to post-process text files to extract runtimes, results, or information about the hardware used for the calculations. I should add here, it's also useful if you are pre-processing data to get it into the correct format. So I think that the skills that you're going to pick up here are going to be useful while constructing your workflows. So the Linux environment provides a wide range of tools for sorting, splitting, and manipulating files, along with tools for extracting content based on location or value. So as I mentioned, we're going to cover split, head, tail, sort, shuff, NL, awk, sed, grep, and paste. Some of these tools have many options. We don't have a whole lot of time today, so we are just going to be looking at the basics. So you might be wondering, can't I just do all of this work by hand? Do I really need to learn yet again something new? And hopefully I'm going to convince you by the end of the hour that these tools are worth spending your time learning. So while the text manipulation task could be done by hand, this process can be time consuming, it can be tedious, and most of all, I think it can be error prone. This is going to be especially true if something needs to be done many times, such as extracting a value from potentially thousands of files generated during a set of parameter sweep calculations. So an obvious solution is to automate the process, and sometimes this requires the development of relatively complex parsers that would be beyond the ability of non-programmers to write, but often these simple Linux utilities are going to be sufficient. So just a little bit more background before we dive into the tools. And I recommend that if you have some time that everybody read this report. Back in 1978, there was a Bell Labs report that laid out the Linux philosophy that is still relevant today. So for example, make each program do one thing well. To do a new job, build afresh rather than complicate old programs by adding new features. Expect the output of every program to become the input to another as yet unknown program. Design and build software, even operating systems you tried early, ideally within weeks. Don't hesitate to throw away the clumsy parts and rebuild. And then finally, use tools and preference to unskilled help to lighten a programming task, even if you have to build a tool and throw it out after you're done. So I'm just going to highlight a few of these. So first, make each program do one thing well. As we go through these Linux text manipulation tools, I think you'll recognize a theme. So for example, sort only sorts the contents of a file. It doesn't do anything else. It's truly a single purpose tool. Head only lists the first few lines of an output. NL only adds line numbers to output. So this is really convenient. It keeps the tools a little bit simpler, a little more compact, and they're very, very good at the task that they were designed to do. Next is expect the output of every program to become the input to another as yet unknown program. And this is really, really going to be helpful as we build more complex workflows. We'll see how the output of one tool can be used very easily as the input for another. And then finally, I highlighted at the start of that last bullet, use tools and preference to unskilled help to lighten a programming task. So you saw my earlier comments about avoiding tedious, time-consuming, and error-prone tasks. Another way to interpret this is don't hire a student or an intern to do your grunt work. Or maybe if you hire a student or an intern, you'll get a really good one who will automate the tedious, repetitive tasks. All right, so regarding the hands-on examples, the accompanying GitHub repos contain examples showing the usage of each tool. You can either execute these in a Jupyter notebook to walk through each exercise, or you could download and execute the scripts from the command line. I think the latter is a little bit better, especially since most of you have an account on one of the access allocated resources, Bridges or Jetstream or Expanse or other machines. So the best way to master these tools is to try new things, deliberately introduce errors, see what happens, extend the examples to introduce new features, chain the tools together to create more complex workflows, and finally, most importantly, this is when you'll really take ownership of these tools, apply them to your own use cases. Look at the things that you've been doing already that you could do more efficiently, the things that you've been doing by hand, opening files and cutting, pasting into a spreadsheet, and see if you could use these tools to replace those, those manual workflows. And with that, we are now going to jump into our first tool. So we're going to start off pretty easy. We're going to look at head and tail. These are tools that you might already be familiar with. So by default, head outputs the first 10 lines of a file, and tail outputs the last 10 lines. So if we go into the directory where I have the head tail examples, you could do a head file.txt, you'll see those first 10 lines. If you do a tail file.txt, you will see the last 10 lines. As you might have expected, the user can override the default and specify the number of output lines. So here I'm going to do a head-n7, and that's going to list just the first 7 lines. I could do a tail-n7, and that is going to list the last 7 lines. Now, one feature that's a little less known is that you can pass negative numbers to head and what I'm going to call explicitly positive numbers, so using the plus sign to tail. So if we do this with head, that means that we're going to, sorry, was it for head? That we are going to list all but those last 15 lines. And if we pass a positive number to tail, it's going to list all of the lines from that line number, in this case 16 onward. And you could actually tie these together. I have an example in the second GitHub repo where I combine head and tail to actually select lines from the middle of a file, say lines 6 through 10. Now there are more efficient ways to do that using sed, but if you don't want to get into the more complex tools, you could use head and tail to do some fairly complex extractions. All right, so now we're going to move on to paste. And this is a tool that I discovered surprisingly late in my Linux career. And once I discovered it, I really thought to myself, I wish I had known this so much earlier, because you can use paste to replace a lot of work that you might have been doing with spreadsheets, where you need to combine data from 2 or more files. So the paste command combines two or more files line by line. Now, by default, we are going to use a tab as a delimiter, but this can be overridden using the -D option. And this is much more convenient than cutting and pasting into a spreadsheet. So again, this example is in the first GitHub repo, and you'll see more extensive examples in that second GitHub repo that I'm developing for the Coursera class. So let's take a look at a couple of files in our paste directory. So we have fruits.txt, has apple, banana, and grape. We have colors.txt, and that has red, yellow, and purple. And if I want to paste these together, again, using the default delimiter, which is a tab, very easy, paste, fruit.txt, colors.txt. And now I've combined the two of those files side by side into a single file. Now, a lot of times we want to work with comma-separated data rather than tab delimited. This is really going to come in handy if we have data that has embedded spaces and we say later want to import it into another program or into Excel. So on the right side of the screen here, again, I show the contents of the two files. In this case, I'm going to add -D, and then within quotes, I have a comma. So now I've combined fruits.txt and colors.txt using a comma instead of a tab as a delimiter. Now, strictly speaking, you don't need to have the delimiter quoted, but I like to do it. I feel that it makes the command a little bit easier to read, especially if I'm going to be saving this and integrating into a larger workflow or part of a shell script. Okay, we're now going to move on to NL. And this is another tool that I discovered surprisingly late, but very, very convenient, very, very useful. The NL command adds line numbers to a file. Now, I'd like to say it's not an essential command since the same task could be done using other tools, but I think it's very convenient and it's much easier than the options that I have at the bottom of the slide. So by default, if I just do NL followed by the file name, it's going to add the line numbers and they're going to be right justified. So I do an NL fruits.txt, I get 1 apple, 2 banana, 3 grape. Now, if you go to the NL man page, you'll see that there are a lot of options for tailoring the formatting of the numbering. So for example, if I do -N followed by one of the format specifiers, in this case LN, I'm now going to get left justified line numbers. We could also go much, much deeper into this. Again, I don't have time to explore all the options here, but you could include 0 padded numbers. You could control the width of the number and so on. And you might be asking, why would I need to do something like this? I could say it would be very, very convenient if you had a high throughput computing workload, say where you had files numbered, say 000 through 999. The reason you might want to have those 0 padded numbers is so that the files, when you sort them, it's going to be much easier. So rather than going 0, 1, 10, 11, 12, 13, so on, and then 2, 20, and so on, you could use the 0 padding. Now at the bottom here, I show a couple of more awkward ways of doing the same thing. And this is something that I had actually done in the past. We could use the sequence command. We could pass an integer value. Here I am capturing in backticks the output of the line count for fruit.txt. I'm redirecting that output into a temporary file, and then I do a paste of that temporary file and fruit.txt. So give this a try if you're interested. It works, but it's much uglier and it's going to be a lot harder to use if you want to control the formatting. You could also use awk, which we're going to be talking about a little bit later in this session. Don't worry about the syntax here. This is a pretty straightforward awk command. But I would say in this case, again, stick to the NL command. And I'm just going to take a quick look at the chat, see if there are any questions here. Whoop. Okay, it looks like we're all right. Okay, so now we're going to look at some slightly more complicated tools. We're going to look at sort and shove. So sort, without any arguments, is just going to sort the contents of your file by lexicographical order. And when I say sort the contents, it's going to treat the entire content, everything on a line of that file, as a single string. So if we go into the sort and shove directory, you'll see examples and files that you could work with. So let's take a look at unsorted1.txt. And hold on one sec, chat. Okay, good, no questions yet. So if I do sort on that file, you'll see that I now get apple, apple, banana, banana, grape, grape, orange, peach, pear. One thing you might be wondering is how are upper and lowercase letters handled. You see in at least when I executed this on Expanse, that the default was to interleave the lowercase and uppercase letters. So here we get apple, followed by uppercase banana, uppercase grape, orange, peach, and pear. I can modify my environment. Here I'm using the export command to set lc underscore all equal to c. This means computer order, or what we call the ASCII collating sequence. And in this case, all of the uppercase letters are going to appear lexicographically before the lowercase letters. So in this case, we get banana, grape, then apple, orange, peach, pear. This is just something to be aware of. This is kind of one of the gotchas with sort. You just need to make sure if you're working with mixed case text that you have your environment set correctly. Now, in many cases, this might not matter to you, but do be aware that it could be an issue. And it can vary from system to system. Now, with sort, we can do we can do a lot more complicated sorting. So I think all of you are probably familiar with using Excel spreadsheets where you can sort in one column, you could sort on another column, you could sort by one column and then sort the results within that sort by a second column. You could also sort by by alphabetical value or by numerical value. So we'll look at a few examples here. So let's take a look at the file unsorted2.txt, and here we have in each row we have a fruit, we have a number, and then we have a food or a junk food, so taco, pizza, hot dog, and so on. Now I can sort on a particular column using the -k option. So the first sort I'm going to do is to sort on that last column. I do a sort -k3, 3 on unsorted2.txt. And here that I see that I've sorted by that last column. So we get the expected ordering: hot dog, pizza, popcorn, pretzel, taco. Now the syntax here is a little confusing. So I didn't just do K3, I did K3, 3. What this means is that I want to restrict the sorting to just that column. Now here, when I'm sorting on the last column, it doesn't matter so much, but if I'm sorting on other columns and I don't have the, I don't have, for example, the -3 or the -2, what it means is we're going to sort on that column and include all of the text that comes after it. So it's usually safer, and typically what you want to do is to sort just on that column. So in this case, I did a -k3, 3. Now, in the box on the right, I decided to sort on the second column. So I did a sort dash K2 comma 2. And you'll notice the results are probably not what you wanted. So you can see if we go down that second column, we have 12, 17, 23, 35, 6. So sort by default is going to sort alphabetically or by the ASCII correlating sequence. And in this case, 1 comes before 2, 2 comes before 3, and so on. So now instead of doing a numerical sort, it treated all of the content in that second column as strings. So it's the string 12 rather than the number 12, and so on. And in this case, sort did exactly what it thought it should do. It didn't know the context. It didn't know that that second column was numbers. But if I add the dash n option, so here I do a sort dash K2 comma 2n, and I could have also had the n separate, another space dash n, that would have worked too. We can see here that we now sorted by, we sorted numerically by that second column. And yes, then I highlight here, lexicographic order versus numeric order. Now, sort can also be restricted to listing unique values by specifying the dash U option. And this is something that I find myself using all the time, where I just wanted to know what are all the unique values in a file. So this is a great way to get rid of duplicates. So here I did a sort dash U in the file unsorted1.txt, and you can see that it has removed those duplicates. So now we just have one occurrence of apple, one occurrence of banana, one occurrence of grape. So very, very useful tool.
Hey, Bob, can you go back one slide? There was a question.
Yes.
Could you repeat what the second number means? There was a small glitch.
Yes, Javier. Yeah. So the second number, So the second number, after the comma, so like the dash K2 comma 2, that means that I want to restrict the sorting to just that column. So what would have happened is if I did a dash K2, that would have meant let's start in column 2 and everything after that. So in this case, I would be sorting on 12 space popcorn, 17 space taco, 23 space hot dog, so on. So in this case, if I had omitted the dash 2, it would have probably still worked okay. But if this was all text data, and let's say in that second column, I had replicated data, let's say, let's just assume that it's strings for now, say red, red, blue, 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 I would then be sorting on red popcorn, red taco, blue hot dog, blue pretzel, and so on. So I could end up modifying the ordering results in a way that I hadn't intended. So Javier, does that answer your question? Oh, good.
Yes, thank you so much.
Oh, you're welcome. Yeah, and this is one of the fine points that you often don't see in many of the treatments of sort. Okay, so let's move on, and thank you, Nicole. All right, and this is, here we're going to dive in to see, the real power of sort. We could sort on multiple lines of text. And I have an example here. I'm going to call it, well, I called it unsorted3.txt. It's really a collection of produce. I have apples, bananas. They come in different colors, red, and green, and they grow in Canada, Mexico, and the USA. So ignore for now the fact that Canada doesn't really grow bananas. This is just an example to illustrate sort. So here, I decided I'm going to sort on column 3 first, and then I'm going to sort by column 1, and then by column 2. So but when I do this, you can see that all of the Canadas come first, all of the Mexicos, all of the USAs, and then within Canada, we see since I sorted on column 1 next, I get the apples followed by the bananas, and then finally the last sort field was the second column. So now within Canadian apples, I have green and red. I could also do reverse sorts. So in this case, on the right hand side, I'm doing a sort on the second column, and I decided to do this in reverse. So now I'm going to get all of the red fruits first, followed by all of the green fruits. Then the next column I sorted on was the first column. So we get within red, we have apples followed by bananas. Within green, apples followed by bananas. And then finally sorting by the country. Yes. Oh, great, great. Thank you, Jasper, for sharing that. All right, so let's move on. Finally, sort has an option to randomly shuffle the lines of a file, but this is one of the real gotchas with sort. Because of the way it's implemented, identical lines are always going to appear next to each other. The Linux shuff utility is a better option. If you want a random permutation of integers, consider pipe being output from seek into shuff. And I realized after I made this slide that shuff actually has an option, that there's a flag for generating random sequences of integers. So look at the example here. On the left, we have a file abc.txt, and it has three A's, three B's, and three C's. And when I do a sort -r, capital R, to get a random shuffling line, we see that we have the three B's followed by the three C's followed by the three A's. And the first time I did this, I thought, oh, maybe it was just just randomly came out that way. But no matter how many times you run this, you're always going to see that that identical lines are going to be grouped together. If you really want to randomize, I'm going to say use the shuff command. And a place where shuff might really come in useful is, to me, the first one that comes to mind is if you are training an AI model and you need to divide your integers or your images or other content into a training and a validation set. This would be a really good way to just randomize that list. All right, so let's move on to split. Now, I think that split is really useful when I'm working with a large amount of data and I want to break it into chunks, each of which could be operated on separately. So I had done this a few years ago for a big bioinformatics project. By default, we're going to get chunks of 1,000 lines using the naming convention X followed by two letters. There are a lot of options to split to specify different chunk sizes, prefixes, and numbering. So here's a case where I use split to break up a FAST file, a type of bioinformatics format, into multiple chunks. And we could see that we have a bunch of files that each have 1,000 lines, and then followed by a file that has 991. So if the file cannot be divided evenly, the last output file gets whatever is left. I could control a few things. So in this case, on the right, I'm saying give me chunks of 2,000 lines instead of 1,000. And then the last argument here, genome underscore, I said, I'm going to override that naming convention, XAA, XAB, and so on, and give these files names that might be a little more meaningful. So here I'm using the prefix genome underscore. So we get genome AA, genome AB, and so on. Now, one thing to be aware of with split is, say you're working with files that have a well-defined structure, is that the default record separator, using the default record separator, may lead to undesired behavior. In this case, we want to keep, say, annotation and sequence together. So we could actually specify a different delimiter. So in this case, I'm using split, breaking into groups of 200 lines. And here I'm making my delimiter the greater than sign. So this changed the definition of what a line is. A line is no longer defined by the new line, at the end of a string, but it's now defined by that greater than sign. Now, one quirk here is that the delimiter is going to be consumed. So if we look at the head of a few of these files, we'll notice that that greater sign is gone. And if you're working with bioinformatics pipelines, this is going to break everything. But I have an example toward the end of this presentation where we show how we can fix that. All right, so I'm going to move on to a few of the more advanced tools. We got about 25 minutes to do this, and it's not nearly enough time to cover grep, sed, and awk. We could do entire workshops in each of these, but I at least want to introduce you to some of the important features. So grep is a tool that I go to all the time when I am searching. Let me just check the chat here. Okay. Oh, great. Thank you, Jasper, for following up on the sort. And Sarong, we're gonna have a open session at the end of the lecture at noon. And if you want to stick around, we can to talk about this in more detail or any other questions that y'all have. All right, so grep returns all the lines in a file containing the search string. Keep in mind that upper and lowercase letters are different characters, and you'll need the -i flag if you want your matches to be case insensitive. So if we go into the grep directory, you'll see that we have a file there. And again, I don't really expect everybody to follow along while we're doing these. You could, if you can watch the presentation and do the examples at the same time, great. Otherwise, I'm going to say do this afterwards on your own. Okay, so we go into the grep directory. We have a file1.txt, and here each line has 3 fruits. And most of them are in lowercase. A few, like the bananas, are in uppercase. So if I just use grep, the name of the string I'm searching for, banana, and then the file name, I will list all of the records that contain banana. Now, in the second use of grep, I explicitly search for banana with an uppercase B. And notice that we returned different lines. And the first two was just the ones that had banana in lowercase. In the second instance grep, it's banana in uppercase. And I could get both of those with one fell swoop if I use the -i to make the search case insensitive. So I do a grep -i banana, and now I get all of the upper and lowercase bananas. All right, there's a really useful option for grep -o if you want to return just the match rather than the entire line. And there's also a --color equals auto flag. And this is going to be the default configuration on many systems, including Expanse, that will colorize the match. So let's go back to our example where we're searching for bananas in file1.txt. I start off in the right-hand panel, grep banana, we get our 2 lines. Now I'm going to alias grep to grep --color equals auto so that the output will be colorized. I execute that same command, and now I get the same output, except banana is going to be highlighted and I believe also in bold. And then the final example, I use the -o flag so that I get just the match. And this is really handy if you're, say, wanting to count occurrences of a string in a file. So in this particular example, banana only appears once in each line, but let's say I had lines that had more than one occurrence banana, apple, banana, banana, or banana, banana, orange. In this case, if I use the -o, I'm going to capture just the matches. Output is going to be 1 per line, and I could get a word count. In fact, if you go to the repo accompanying the Coursera class I'm developing, you'll see an example of how you can use grep and WC to actually calculate word frequencies for a file, and with just a few simple commands. All right, another useful feature of grep is that you can print the context of the match. So there's a -A, a -B, and a -C flag. And I'll just show the A and the B flags here. So in that first use of grep, grep-b3 kumquat file1.txt, here I want to print the 3 lines before the matching line. So think the capital B as standing for before. So now we can see for my match, I've got the pair kumquat grep, and I have the 3 lines that are preceding it. Now in the second example, I use a grep-a2 kumquat. Now I can print the 2 lines after the matching line. So here I get pair kumquat grep followed by 2 lines. And I could also use the -C option, which will give us the context both before and after. Now where this is really, really helpful, being able to search for the context, is let's say you've done a calculation, you've run a molecular dynamics or a computational chemistry code, and you know that there's a particular line of output with a certain pattern, and you know that you want whatever comes in that following line. So this would be a really convenient way to extract that information. grep can also do an inverted match to print lines that do not match the pattern. So on the left here, I'm searching for lime in all of the files in the directory. We see that I have a couple matches in file 1, 3 matches in file 2. If I do a -v, in this case grep-v lime star, I get a list of all of the lines that do not contain the match. So everything that doesn't contain a lime. Other options include printing the names of files that contain or don't contain the match, and listing the counts of matching lines. So here again, I'm going to do a grep lime star, so I see a few matches in file 1, a few matches in file 2. If I do a grep-c lime star, now I get the number of matches in each file. Now keep in mind though, this is the number of matching lines, not the actual number of matches. Think of the example we're talking about where the matching string might appear multiple times on a single line. In that case, you might want to do a grep-o lime and then pipe the output into a wc-l. We could also list files that contain a match. See here we have a grep-l kumquat. And so this means, file 1 did contain kumquat. I could do a -L to list the files that don't contain the match. Okay, up to this point, our pattern has been a string literal, for example, lime or banana, but grep can recognize more complex patterns that use character classes, anchors, and even regular expressions. So we're not going to get into regular expressions here. We have a whole nother webinar on that where we get into all of the details of regexes, but we're just going to look at a couple of useful examples here, and that is anchors. So again, my first grep example is I'm searching for all occurrences of pair, and we can see in file 1, there's twice what appears at the end of the line, twice what appears at the beginning of the line. I could use an anchor, that caret symbol. So I do in quotes, caret pair, and now I'm only finding the lines that start with pair. Likewise, if I use a dollar at the end, so I have in quotes, pair dollar, now I'm getting all the lines that end with pair. So again, that's barely getting into regular expressions, but there's much more that you can do. All right, so we're going to move on to sed. Now, sed and awk are extremely powerful. They're very complex tools. We could easily spend days exploring sed, and entire books have been written about it. So if you're really interested in sed, if you want to do a deep dive, there is an O'Reilly book. Great big, thick, dense book that covers just sed and awk. We're not going to go there. We're just going to show you a few examples of the way that sed and then awk are commonly used. But if you're interested, there are books. If you go to SourceForge tutorials, you'll see all sorts of examples of really dense sed expressions. But what we're going to do is focus just on the most common use of sed, and that's to apply a substitution to each line of a file. And this is something that I could see being really, really helpful. Again, if you have a high throughput computing workload, we have, say, an input file, and we want to have many, many instances of that input file that, say, all differ by just a single line or a single parameter. So we could write a bash script using sed to easily generate many, many instances of that file rather than having to copy it and go in and manually edit each one. Now, an important thing about sed is that it's a stream editor, and this will actually let you do things that you might not have been able to do with VI or Vim or Emacs or Nano, because when you use those editors, you need to load the entire file into memory. Sed is a stream editor, which means that it works on a stream of data, and the entire file does not need to fit into memory. So it will read the file one line at a time, or probably under the hood one chunk at a time, a very reasonably sized chunk, and do the transformation. So you can use sed potentially to work on files that are many, many gigabytes in size, and it will be fine. All right, so the most common use of sed is the first two examples that I have here, where I use the S command for substitute. And then notice the syntax. I'm using forward slashes, replace the first occurrence of this with this, and then followed by the name of the input file. And then the second example, and this is one of the gotchas with sed, is I have a G at the end there, which means global, which means replace every occurrence of this with that. Now, sed allows us to also integrate patterns. So just like we did with grep where we're searching for a pattern, we could ask sed to restrict its behavior to lines that match a particular pattern. So in this case, I added, again, here within slashes, the pattern that we want to restrict to, and then followed by the substitution. All right, so here we're looking at a few examples of sed. On the left, we're going to replace the first instance of pair with XXXX. And we're going to apply that to file one. So we have sed, and then in single quotes, s/pair/ 4x's/ and then closing quote. And you'll see that there were some places where we replaced pair, but in the last three lines, we actually had two occurrences of pair. So for example, in that third line, we had pear, apple, pear, grape, and notice that only the first one was replaced. And in the second example, on the bottom on the left, we used the G flag so that we do a global replace. And now you'll see all occurrences of pair have been replaced with 4x's. Now on the right-hand side, we look at something that we had done earlier with grep, where we use anchors. So in this case, I want to replace pair with XXXX, but only if it appears at the start of the line. And then the bottom example on the right, I want to do that replacement only if it occurs at the end of the line. Now, here we're using anchors. This is one of the simplest examples of a regular expression. But if we know a little bit more about regexes, that stuff between the first two pairs of slashes could be an arbitrarily complex regular expression. All right, so I mentioned also sed can restrict the transformations, the lines that contain a specific pattern. So, we start off for doing a global replace of pear with orange. But in that second block on the bottom, notice within the single quotes, I start off with /grape/. And what this means is I'm going to do that substitution, pear replacing pear with orange, but only if the line contains orange. Only if the line contains grape. And you'll notice that these substitutions were not done on those last two lines. Okay, sed can also be used to print out specific lines. So we're going to use the P option to do that. So, oh, I forgot to mention here, the dash n means suppress printing so that we don't print every line. That's gonna allow us to restrict the printing to certain lines. So I'm not gonna go into the details too much here, but a few examples where we print the fifth line, lines 3 through 5, and every third line starting at line 2. And I know the syntax, especially for the last example, is a little dense. Not entirely obvious. Okay, I want to point out one of the gotchas with sed. Like all other commands that write to standard out, sed output could also be redirected to a file, but there's just one gotcha, and that's that if you want to do a replacement in place. So remember that sed streams through the file rather than storing it in memory, and redirecting it to the original file is not going to work. Either write to a temp file or use the -i option to edit in place. But do be aware though that if you use the -i option, it's now going to be requiring sed to potentially hold that file in memory. So, we look at an example here. Let's get the first 2 lines of the file 1.txt. We'll redirect that into a new file. And now I'm going to do a substitution, replace pair with 4 x's on that file. And then I'm going to redirect the output into that original file. And we can see when we go to cat that there is no output. But if I either redirect into a temp file or use the -i option to edit in place, then I get the expected result. So again, just one of the gotchas was sed. All right, we are getting very close to the end, and I'm going to kind of rush through awk. Awk is actually my favorite tool. I go to awk a lot more than I do to sed. The name comes from its 3 creators, Aho, Weinberg, and Kernighan. Again, covered just like sed in this very thick, very dense O'Reilly book. But we're going to focus on just the most common usage. Now, awk is actually a pattern scanning and processing language, not just a tool. So if you look at the text I have at the bottom, awk is a full-fledged programming language with arrays and control statements and other advanced features. And we're going to ignore all of that for now. I'm going to say that you rarely see awk programs in the wild, since they've been displaced by more widely used languages, such as Python. Where awk is used a lot, though, is in these one-liners that we're going to be demonstrating. So a awk program consists of one or more rules containing a pattern, which we've seen already in sed, followed by an action. The syntax is important. The pattern is always between forward slashes. The action is always in curly braces. And the whole rule is enclosed with single quotes. And there can be multiple actions separated by semicolons, and there are special actions that we'll talk about in a few slides that are executed just once at the start and the end of the execution. So the most common use of awk is to print or extract selected fields from a file. Awk processes one line at a time, split into fields referenced by position, $1, $2, and so on, and the last field can be accessed as $NF, where NF is the number of fields. So if we go into the awk directory, you're going to see a file, people.txt, and I just listed, I think it only has 4 rows. So there's a person, a pet, a food, a fruit, and a color. And let's say that I wanted to extract the first, the third, and the last column. So in this case, we're going to get the name, the food, and the color. So I use awk, and then my rule, again in curly braces, is going to be print $1, $3, $NF, and we can see now I get those 3 columns. We get Bob Meatloaf Blue, Cindy Pizza Purple, and so on. Now, in that previous example, we really didn't need to use the NF variable because every row had 5 fields. But sometimes we're going to be working with ragged text, or we don't know we don't know how many fields are in each line. So if I look at the ragged text field, we see that we have, sorry, in the first line, 3 fields, then 2, then 4, then 1, then 5. And if I wanted to print just that last field, I could do a print NF, and I get the last field in each row. Now, awk can also take a search pattern and include other text in the output. So in the first example, I wanted to make the output a little more readable. Instead of just listing a person and a food, I decided we're going to add some intervening text. So Bob favorite food is meatloaf, Cindy favorite food is pizza, and so on. So notice how I put a literal string in there. In the bottom example, I wanted to limit the output to lines that contain pizza. So here I did an awk, and then my pattern is pizza, again in forward slashes, and I'm going to print the first and the third field. So now we get Cindy pizza, Susan pizza. Now, by default, awk uses white space as the delimiter, and I find this really, really convenient. Some of the other tools are a little pickier. They might use, for example, tabs or single spaces. Awk is really, really flexible. But there are times that when using white space as the delimiter, it might get you in trouble, especially if you're working with comma-separated value files. So let's look at the states.txt file. And here we list a state, the capital, the state bird, and the state flower. And they're all comma separated. And notice that some of the birds and flowers, and even the state names, have embedded spaces. So for example, the Florida state flower is an orange blossom. New York as a state has an embedded space, and so on. So I could change the delimiter. Here I'm going to do dash capital F. I'm going to have my delimiter, in this case a comma. Again, I don't believe that the quotes around the comma are required, but I think that it makes the command a little more readable. Awk also provides basic math capabilities. You could do square roots, logarithms, exponentiation, trig function, even random number generation. This is a case where I have multiple actions separated by semicolons. So in the first example, what I'm doing is calculating the sum of the first two numbers, the product of the first two numbers, and then I'm going to print out the first number, the second number, the sum, and the product. And then the next two examples just show how I could calculate sines and cosines. Not going to go into the detail here. We're running out of time. But if you're familiar with C programming or ever used printf, you could actually control the formatting to a very, very high degree of precision. Finally, one last thing I want to show with awk, and this is incredibly, incredibly useful, is if you want to calculate a sum or an average over a column of numbers, you could do this very, very easily. Here I'm using S1 to sum the value of the first column, S2 to sum the value of the second column, and then at the end, I do a print. I take S1 divided by NR, a predefined variable containing the number of lines, S2 divided by NR, and voila, I've calculated the averages for each of those columns. And much easier and more convenient than pasting into a spreadsheet. And then, I did mention that awk is a full-fledged processing language. And just want to show an example here of how we could use if or if-else constructs to control the output. So in the first example, I print line only if the number of fields is greater than 2. In the second example, all I'm doing here is a sorting. I'm taking those two numbers. If the first one is greater than the second one, I'm going to print them in reverse order. Otherwise, I'll print them in the original order. Okay, so we have a bunch of case studies, and we are at the top of the hour, so I'm not going to go through those, but I encourage you to look at these. These were cases where I used some of these tools in real life. The first two examples are from the reliability testing for a couple of our supercomputers, Expanse and Voyager. So you can see how we could take these tools, we can integrate them into bash scripts and do some really useful work. So with that, I'm just going to say one thing about LLMs and we're going to wrap up. Now, LLMs can help. I use them all the time, but you still need to know a bit about the tools and their capabilities. I like to think that without some basic knowledge of these tools and what they can do, it's hard to even know what question to ask. So here's an example where I asked ChatGPT to give me an awk one-liner, and it did a pretty good job. And then another one where I asked it to give me a sort command to sort second field numerically, and then after that by the first field in reverse alphabetical order. And it gave me a very helpful sort command. But again, you need to know what these tools can do in order to even ask the right questions. So conclusion, Linux has a powerful suite of tools for text manipulation. They can make you more productive, reduce the likelihood of errors. Don't be discouraged if you didn't understand everything. We covered a lot of material in a short amount of time. Work through the examples at your own pace. This was really too much to cram into a 1-hour webinar. For some of these tools, we barely scratched the surface. If you enjoyed today's talk, be sure to come back when we dive into regular expressions. And finally, LLMs can help, but you at least need to know the basics so that you can formulate meaningful prompts and understand the output of the LLM. So with that, I am going to stop sharing and I am happy to take questions. And sorry, went over just a couple minutes over.